record here. All right, welcome everybody. This is the Soil, Water, and Climate Department Seminar. My name is Kelly Wells. I am a research scientist in the department and one of the co-organizers of the seminar, along with Basu Sharma and Kyle Shervine. And before I introduce today's speakers, I just want to say that our next seminar will be 1 week from today on November 17th. It will be Dr. Sarek Matson, who's a postdoctoral researcher in the Toner Lab in our department. And he'll be speaking about phytoremediation of arsenic in urban agricultural soils. So please join us next week for that. But today I have the pleasure of introducing our two faculty lightning speakers. We have Peter Neff, who is an assistant research professor in the department, and he'll be talking about plans to expand the Western Antarctic ice core array. And then we will have Kyungsoo, who is a professor in the department, and he'll be talking about his group's research on mapping earthworm invasions and also on mountain farming. So Peter, I will go ahead and turn it over to you.
Great, thanks. I'll share my screen here and get started. So hi, everybody. Thanks for the opportunity to share a little bit of what I am thinking about with everybody. And I know this might be a little left field for what folks in the department do. So I'll try to give good overview of Antarctica and the importance of Antarctica in all of our future. So my work has been through my career, working primarily with Antarctic ice cores and also ice cores from southwestern British Columbia. But I have ambitions that I'm sort of pushing on here to expand our existing observational array of ice cores in West Antarctica to capture climate right on the coastal regions where we have very, very few observations and where most of the change in Antarctica is underway. So hopefully give you enough interview here. So let's go to Antarctica really quick. So Antarctica is this, big, mysterious seventh continent, highest, driest, coldest pile of snow that's surrounded by the Southern Ocean. And every winter, the area of Antarctica doubles in size as the Southern Ocean freezes over and forms sea ice, which then melts away almost entirely every summer. This is a big place, so it has a lot of control on some really important processes in the Earth and climate system. So that's why we care so much about it. And its size and its remoteness obviously makes it pretty difficult to observe as well as we would like, both in space and in time. So that's sort of our classic problem in Antarctica. We haven't been there very long. It's hard to be there, and it's hard to observe even from space with satellite platforms. And so my work sort of has a role in all of those things, increasing our observations and our understanding of Antarctica in space and in time with ice cores. So if we hop down on the surface of Antarctica, certainly there's plenty of snow to go around. Antarctica is simply a pile of snow that is compressed into ice because it never melts. And I'll quickly give you the answer to this question, but it can be sort of surprising how thick on average the Antarctic ice sheet is. So it is on average about 1.3 miles thick and up to about 3 miles thick at its thickest point in East Antarctica. And so if all of that ice melted, it would raise sea levels globally by about 200 feet. So that makes it really important. Even small changes in that huge amount of ice have a pretty big effect on sea level. So that's why we want to keep really close eyes on the continent. I thought looking more closely at the surface of Antarctica might be a good way to relate to some folks who might look at soil profiles and things like this. So this is our profile of the top 150 meters of a glacier or an ice sheet like Greenland and Antarctica. So at the surface, you have fluffy snow crystals, snowflakes that pile up year after year. And after about 10 to 20 meters, they start to compress and are slowly turning into pure ice with air bubbles that were once that airspace between the fingers of snowflakes. So by anywhere between 60 and 110 meters depth, we have the full transition to pure ice, and that's where we trap these air samples that are one of our our best record of past atmospheric composition. I'm not really talking about that much in this presentation. And then, of course, in this 150 meter top surface of the ice sheet, that's sitting on another 1,000 to 2,000 meters even 3,000 meters of ice below it. And so as we observe, especially from satellite platforms, the Antarctic ice sheet, we're observing all of these processes from the full thickness of ice that's flowing under its own weight, but also we're observing the snow surface and compression of the surface snow. So if we look at a sort of extreme example of how a snow surface changes on a glacier in a mountain region, this is a time lapse over a couple of months at one of my mountain glacier sites. And you can see the snow surface is dropping through the warm season due to that compression and some partial melting of the snow surface. And so as you're observing from satellites above, the height of that surface, like NASA does with some fantastic satellite platforms, you have to take into account that what we call the fernification process, the process of compacting multi-year snow. And we really need ground observations for that, and ice cores are a fundamental way we get that information. And so one of the best ways we know the Antarctica is changing is from these satellite platforms that we need to validate with ground observations. So if we take a look at that, zooming in on Antarctica and West Antarctica in particular, we see that along the Pacific coastline of West Antarctica, and we call it the West Antarctic ice sheet, or WAIS is our sort of glaciology community's colloquial for the West Antarctic ice sheet. The outlet glaciers and the ice shelves where those outlet glaciers go afloat on the ocean, that is where Antarctica is losing most of its mass. It's caused by ocean-driven warming underneath ice shelves. So the way Antarctica works is snow falls in, it flows out to the coast, and it calves off in big icebergs or melts from below these floating ice shelves. There's very little surface melt in Antarctica, which is quite different than we observe in Greenland. So again, this is an observation from satellite altimeters, ICESat and ICESat-2 that NASA has operated since the early 2000s. And to get this ice thickness change, observations like this include all of those processes from surface snow compaction to the full 2-mile thick ice flowing out to the sea and thinning. And so capturing all of those processes is critical to understanding the Antarctic ice sheet today and how it's going to change into the future. And to illustrate the importance of that, there's a recent paper that's come out around the COP26 negotiations, but we still have the opportunity to avoid widespread collapse of the West Antarctic ice sheet, which is the vulnerable part of Antarctica, if we keep global warming below about 2 degrees Celsius. So on the left there is a low emission scenario, the RCP 2.6 to use the lingo there, but a really aggressive societal actions to reduce emissions. We can keep sea level rise from Antarctica to about 1 meter by the year 2300. So looking out a little further than we usually do. Most of these projections, we sort of look at the 2100 timeframe. If we really amp things up and don't do anything to reduce our emissions, so this is the RCP 8.5 scenario on the right, you're looking at 2 to 3 meters of sea level rise just from Antarctica by the year 2300. So we have long-term commitments here, and we still have the opportunity to prevent really huge amounts of sea level coming from Antarctica relatively soon. And so my work is sort of positioned around best understanding that by sort of running towards the fire, running towards these red regions. And I put these extra red dots on here so that, sorry, I didn't explain that the open red circles are existing, basically our climate observations. So we only have one weather station in West Antarctica that's sort of in the center of that cluster of open circles. It's been there since the 1950s. And on the coast, typically the coastal regions are quite complex for ice coring, but we have these features called ice rises, sort of 500-ish meter thick stacks of ice or of snow that sit right on the coast in our ideal ice core sites. And so they're experiencing the conditions that are changing these floating ice shelves and putting West Antarctica at risk. And so I'll be talking about these locations for the rest of the presentation for the most part. So in this warming world of ours, we need to understand as temperature is rising and those rising temperatures are changing the structure of the atmosphere, we need to know how that's going to affect all of these processes that are pushing around the Antarctic ice sheet. So surface mass balance, SMB, is what we call snowfall, the main input into the bank account of Antarctica. We need to understand ocean current upwelling, how relatively warm water is getting under these floating ice shelves, underneath these ice shelves, right? We can't actually see this process in a direct way. And all of this is focused on making sure our projections of sea level rise going forward are as accurate as possible so that we can choose to avoid worse outcomes and so that we can start adapting to the most likely scenarios for sea level rise. I really like the way that some colleagues of mine put this. So in order to best understand Antarctica and West Antarctica, we need long-term observationally based reconstructions of whatever climate variable you're interested in and whatever variables matter. So temperature or snowfall in Antarctica is really obviously an important one, and we can't directly measure snowfall like with weather stations in Antarctica because of the nature of drifting snow. So ice cores are our way to get those sort of long time series. And we need those so that we can capture any significant trends that are observable over the extreme noise in the climate in Antarctica, and so that we can quantify the role of Antarctic ice sheet on sea level change, and also better tease out the relative importance of the sort of very scientific language here, but the thermodynamic versus the dynamic changes that are caused by global warming. So thermodynamic changes, meaning that if you increase the temperature of the atmosphere, it can hold more moisture. So we might expect more snowfall to accumulate in Antarctica. But at the same time, the structure of storm systems is changing in parts of Antarctica due to how that extra heat changes the structure of the atmosphere. So all to say, there's a lot going on, and a lot of us across many disciplines are trying to best understand all of these processes. So ice cores, besides just being the tool that I'm familiar with, they're really critical observations of this complex system that can help us with this fundamental Antarctic problem, is that we're limited in our observations in time and or space. So this is sort of our best climate information from the year 1800 to the year 2010 or so. At the top there from our one weather station we have in West Antarctica beginning in the 1950s, Byrd Station, which shows clear warming since the 1957. And then our array of ice cores in central West Antarctica, we have this water stable isotope proxy, Delta 18O, oxygen stable isotopes. That is essentially a temperature proxy that's a little bit more complex than that. But this allows us to put in context that trend from the 1950s, put extreme events in context, and keep an eye on any more emergence of a very clear human warming fingerprint, which there currently is not in a lot of Antarctica besides the coastal regions. Our best data sets besides direct observations from ice cores in Antarctica are climate reanalyses. So these climate model frameworks that assimilate all of the global observations that we have, but they aren't very good in Antarctica before the year 1979 when we had widespread satellite coverage. And so again, ice cores play a fundamental role here in taking us further back in time and giving us a longer time perspective from additional locations on sort of climate across Antarctica. Okay, so capturing variability, emergence of trends, contextualizing extremes, and then also validating those remotely sensed observations from satellites. Okay, so that's sort of the introduction quickly, and I'll try to sort of go through this stuff. I want to just give everybody a sense of what I'm thinking about. So if you are interested in chatting about it or collaborating, that you sort of know where I'm coming from. So my main ambition is to expand our ice core array to coastal sites, but we also need to update our existing ice core array to make sure that it's most useful. So I want to take you again back to Antarctica to show you what this looks like and how the coast is different from inland. So we've been drilling cores in this upper right-hand part of the cross-section of the ice sheet here. The flat, sort of easiest interpretable locations in Antarctica, and where I want to push us to are these sort of miniature ice sheets, coastal domes, coastal ice rises on the Pacific coast of West Antarctica. And so we can fly out there, and these are some beautiful photos from mapping flights back in the 60s. So this is flying from the inland of Antarctica, where there are a few volcanoes there poking through the ice sheet, and then flying out to the ocean that's changing the ice sheet today. So everything is quite flat in Antarctica, despite it being the highest continent on average. And so this is looking towards one of these ice rises that sits right on the coast, right where the ice, ocean, and the atmosphere are all interacting. And these are 500-meter thick stacks of snow, each year snowfall, going back certainly thousands of years. And so this is where I think we need to expand to. We're not sampling these low elevation regions where all of the interactions are happening that are pushing around and jeopardizing the future of the West Antarctic ice sheet. And so these ice rises are just perfect spots for ice cores. that might be slightly more complex than inland ice cores, but they're much more directly sampling the complex processes that are changing the ice sheet. So this is a radar image from airborne observations that NASA made through a campaign called Operation IceBridge that I and my student Julia are working with quite a lot. So I'll just show you again some of these features. These are time-lapse satellite radar image time lapses of some of these locations that sort of just show how these ice rises are located right at the dynamic interface between seasonally frozen ocean and the currents and winds that are pushing around Thwaites Glacier in particular. It's the one glacier that looms largest in our concern for the West Antarctic ice sheet. And through these airborne campaigns, we actually can start to investigate these places, even though they're some of the most difficult regions to access in all of Antarctica. So we can get surface accumulation rates from these radar images. You can see on the right hand of that radar image, you can see all the layers of each year's snowfall, thick layers on the right-hand side, which is the windward side where storms crash into the dome, and then a lower snowfall on the leeward side. So we're starting to learn quite a bit about these places through these airborne campaigns. They were flown from 2009 to 2019. It's big jet flying just about 1,500 feet above the ice surface with radar instruments to see into the ice. So this is the campaign that Julia is working a lot with NASA funding to build snowfall time series remotely in these places where we would love to have ice cores, but we just can't get there quickly. And so we can start building time series, multi-decade long annual time series of coastal snowfall, despite never being to these sites. So the way Julia is doing this, so she's first just sort of validating the method or reproducing the method of a colleague at NASA at inland sites where the layering is nice and flat and simple, counting these layers based on the brightness of the radar return, stacking them up. So these yellow dots here are her annual layer picks. And if we know the aircraft flew over this site in 2016, that's the first, the age of the first year, the first layer, sorry. And so now she has a time series. So on the left there, from 1979, the beginning of the climate reanalysis data set period being good in Antarctica, to 2016 or 2015 when the site was overflown. And so this is gives us a lot of information and allows us to start validating modeled products like the reanalysis. So if we plot the reanalysis snowfall on here, in addition to the radar ice layer thickness, you can see the agreement is quite good. And this is still sort of back of the envelope. Julia's actively working on this. And we validate the method at sites where we have ice cores on the ground as well. So if we put that on the plot, these ice cores that were collected in the year 2000, 2001, you can see pretty good agreement there. This ice core is something a little bit funny with it that we're still working on, but this is the current stage of Julia's work, and then she's going to push out with support from NASA to look at these coastal sites and see if we can start building time series like this, where we've never had ground-based observations, to make sure that our reanalysis products are getting the snowfall amounts right. That fundamental input to the ice sheet system is snowfall, and that's a really not a very trustworthy variable in global climate reanalyses. Okay, so my job, while Julia is plugging along, doing what we can from airborne observations, my job is to propose our first field site in Antarctica. So this is flying across an ice shelf called Sulzberger Ice Shelf, and these features are quite subtle, these little humps of ice. But this is a place called Guest Peninsula, which I think is the first most feasible site that we're hopefully going to be able to get to by the year 2023, 24. And so I know I don't want to eat into the time for Kyungsoo, so I'm trying to wrap up here. But this is something I'm trying to get done in the next month, or certainly by the end of the calendar year. But our ice core projects, if we limit ourselves to drilling to about 150 meters depth, we can do that really, really quickly with pretty tricky logistics and weather constraints. So we need to be fast. We can't drill much deeper than that without having technical issues with coring and ice that's at high pressure with that depth. We know from the snow radar data that NASA overflew there in the bottom left that the snow accumulation is about 0.5 meter per year, which is quite high. So high resolution. We can get a lot of samples in 0.5 meter of snow. It limits the amount of time in an ice core, but in 150 meters, we would expect this site to be 400 years old at 150 meters depth. And that gives us a really great time window to think about climate down there. So you're capturing multiple cycles of any Pacific multi-decadal variability. And so cycles, El Nino is really important for this part of Antarctica, being at the very southern end of the Pacific Ocean. So this is the first site that we can access relatively feasibly from our main logistical hub, McMurdo Station. And Antarctic logistics are really backlogged right now due to COVID and some big projects that they committed to right before COVID. So this is a sort of pie in the sky at this point. It might be delayed beyond 2023, but we're giving it a try. And I don't have much time to talk about this, but I think the concept is pretty simple. So we have all of these existing ice cores, the open red circles, and as these places become out of date, right? We drilled most of these ice cores in some really great campaigns in the late 1990s, early 2000s. So all of these ice cores are 20 years out of date now. So if we drill any new ice cores and we want to compare them to the array of cores across West Antarctica, we can't do that for the most recent 20 years of any new ice core. And so that already we're having some issues putting in context, warm decades. So the 1990s were quite warm in West Antarctica, but we start to drop off in that plot at the bottom there. Our number of ice core records is lowest actually in the most recent years, because it's really just hard to go back to ice core sites and collect the last few years of snow that have accumulated since you drilled your deeper core. So it's a problem, and it is tricky to fly out to each of these spots, being hundreds of miles from anywhere. But the coring is very, very simple. So the snow accumulation across Antarctica is very low. Even here in West Antarctica is considered the snowiest part of Antarctica, but it snows about 30 centimeters per year. It's been 18, 20 years since these sites were visited. So at any of these sites across inland West Antarctica, we can just take a hand auger, a very simple coring instrument, and in a couple of hours collect the 10 or 15 meters that are needed to get back to that year 2000 surface, and then collect about 10 years of overlap with the previous core. So very simple proposition. Sometimes this sort of work can be tough to get funded because it's not that exciting new science. It's maintaining an observational network, but that's obviously a crucial aspect of how we observe so many systems. You have to have continuous, well-maintained observations. So I have a timeline for this. It's great that Julia was able to get the NASA Finest Fellowship to support the rest of her PhD. So I'm super proud of Julia for that, especially during COVID. And I'm working on getting a proposal in by the end of the year for our first field project. And then I think it's a good chance by the end of the decade, we could have an updated array that's expanded to a few of these sites on the coast. But it is a bit of a slow endeavor getting in, with all of the Antarctic logistical constraints. So I'll stop there. Hopefully there's time for a couple of questions, and Kyungsoo will have plenty of time. But it's exciting to think about these new sites, but to make them fully useful, we need to also maintain our existing ice core sites. So I think there's plenty to do there for at least one person and a couple of grad students. So thanks.
Thanks, Peter. That was great. If folks want to either unmute or type a question in the chat, I'll keep an eye on that.
Peter, this is Satish Gupta. I got a question for you.
Mm-hmm.
Say, you said you're going to drill the cores by hand?
Shallower cores to update the existing array, yes. We have hand augers where you can drill 1 meter at a time with, it's a simple sort of T handlebar. But to collect a couple 100-year-long core, that's bigger equipment that we need one drilling engineer to support, but still relatively light. We fly in small fixed wing aircraft to get out to these sites.
Well, one of the things that I saw in your data, you mentioned that there's only one weather station over there in the middle of the Antarctica. Don't you think you guys need more stations over there? Even if you find some depth, what the year is, but you wouldn't know what the temperatures were.
Yeah, so we have very few points of long meteorological observations. So it's simply because the big international push to get research going in Antarctica didn't happen until the International Geophysical Year in 1957. So that's the one place where we have a continuous station, almost entirely continuous from 1957. And then we have scattered automated weather stations that are sort of sprinkled across West Antarctica, including on the coast, but they're very short in time and they have gaps in them. So we do have some constraints. There was a Russian research station out on that really remote coastline, but only during the 1980s. So there's just a lot of incompleteness, and that is just the story of Antarctica.
So you think you'll be able to put together a temperature series for the areas where you want to get the course?
Yeah, it often ends up being somewhat relative. So you get a lot of information about the year to year, the interannual variability, and it's maybe a little bit harder to put an exact number on the temperature, but we can calibrate it to nearby weather stations, even if they're only a couple of years long. And for deeper ice cores, we do have very direct ways to measure the temperature. You can actually measure the physical temperature of your borehole. And at the sort of middle depths in the ice sheet actually still remembers being in the last ice age. So you can actually measure the physical temperature with a little bit of uncertainty. Certainly there's some uncertainty, but it's actually a direct measurement, just like if you put a frozen turkey in the oven, which nobody should do at Thanksgiving. The center of it is going to remember that it was in the freezer, even though it's been in the oven for a couple of hours. So the ice sheet does that as well. It's a great way to get direct temperature.
Thanks.
Well, and if people don't have questions now, and to make sure Kyungsoo has his time, just feel free to shoot me an email at any time. If I didn't talk that much about sort of the geochemistry that we do with ion chromatography and ICP-MS measurements to actually get the proxy records we get for ice cores, but that obviously is a big part of my work besides just the big concepts.
That sounds great. Thanks, Peter. I see there's a few accolades in the chat as well. All right, Kyungsoo, are you ready to take it away?
Okay. All right, let's see here. Okay, do you all see my screen, my PowerPoint?
Yes, we see it.
Okay, great. Okay, so the RAS is going global today because Peter just covered Antarctic. I'm gonna cover the Arctic, so it will complete the global coverage. So it's very nice to see you all, and I'm Professor Kyungsoo, and it is also great to have this opportunity to introduce some of the work that is going on in my research group. I will first talk about our research on earthworms, and then move on to mountain farming. But instead of detailing the findings and results, I will just focus on giving you a very rapid overview of our interest, and also our focus on generating your interest in potential collaboration. So please feel free to talk to me when you see me in the hallway if you see anything interesting in my talk. And also, this is a lightning talk, so I will move at lightning speed. So over the past 3 years, my research group has been mapping the distribution of exotic earthworms in Alaska. So here, when I say exotic, I'm referring to earthworms of European origins. In Alaska, the default situation is no native earthworms, but there is a little bit of a debate about it, but I will not go into the details. So Alaska is huge, and there's simply no way of conducting detailed earthworm survey. So, but we, however, managed our Earthsome survey by focusing on 5 different regions in Alaska that cover a wide range of climates and human activities. So those regions include, and I will go from the south, Juneau area and Kenai Peninsula and Matanuska Valley around Anchorage, and then Fairbanks and Delta Junction in interior Alaska, and then Nome and Seward Peninsula, and then finally the south-north transect along the Dalton Highway. So we went all the way to Toolik Research Station to see the presence of earthworms. The Toolik Research Station is located about 170 miles north of the Arctic Circle. Now, so far, every student in my research group has participated in this fieldwork, but notably, Adrian Wackett and Tyler Bowman have spent cumulatively more than 2 months in Alaska, and they traveled together to remote part of Alaska for last couple of years. So much of what I will say today are based on what Adrian and Tyler found after a lot of extensive and sometimes really laboring fieldwork. So I really appreciate their contributions to this work. So in this, first ever attempted mapping, surprised us in many ways. We are surprised because exotic earthworms are already quite widespread in Alaska. And we are paying particular attention to geoengineering earthworms, and those are the subgroup of earthworms that make dramatic changes to soil structure and biogeochemistry in a matter of a couple of years. So those geoengineering earthworms are rapidly expanding into boreal forest in Kenai Peninsula and Anchorage area and Juneau regions that are along the relatively highly populated southwest coast of Alaska. And then in the interior Alaska, and then the presence of those geoengineering earthworms are often limited to relatively warmer, unusual places like hot springs. So I tell you that we also visited hot springs in these field trips. But in the north of Arctic Circle, we have not found earthworms yet. But according to the local residents in those remote villages, they have been actually trying hard to introduce earthworms to their vegetable gardens. So it may be a matter of time as the climate warms up, their effort may indeed result in some of the settlement of exotic earthworms above the Arctic Circle. So this broad survey over the last couple of years has now informed us how earthworms are being introduced and what environmental conditions limit their settlement and further dispersal. So briefly speaking, human culture and climate are the first order control. So where climate is mild enough to allow earthworms to survive and then invade into the neighboring forest, then vegetation and soil properties begin to filter out what earthworm species survive and then further capable of invading into the surrounding forest. During those trips, we also established quite a few earthworm invasion chronosequences across a large climatic gradient in Alaska. So here's one example from the Stormy Lake in Kenai Peninsula. Nyclurus were introduced here in 1980s, presumably as a fishing bait. And then since then, those Nyclurus have invaded from the boat launching into the forest by about 100 meters. So here you don't really have to be an expert at all to really see and document the impacts those night crawlers have on the soils and on the forest floor. The 20 centimeter thick O horizon have disappeared in this boreal forest, and the new A horizon have replaced the O horizons. The earthworm-free soils are very soft, if you walk on it, but the earthworm-infested ground is hard. So you can even tell the transition by walking on the ground blindfolded. So here's a photo from this summer. So I did my best to find the best photo of Tyler Bowman. And so here, Tyler just found iButton, which is a temperature sensor that we buried here 2 years ago. So he was looking for those iButtons with his metal detectors to retrieve the temperature data over the two last years. So we're interested in knowing how earthworms are changing the temperature regimes in the soils. So far, we have collected soil temperature data from a number of earthworm invasion transects. And those sites include Minnesota Arboretum, which is within the metropolis, and Minnesota Itasca State Park, and several places in Alaska. And also, Adrian and Jonathan Klaminder, who is also my close collaborator, they have also collected quite a few temperature data from earthworm invasion transect in Sweden. So here's one example from Itasca State Park that Sarah Bauer has collected and plotted. So it has temperature data from different soil depths over a time period of a year. So the summary is that earthworms, when they remove O horizons, and make the shallow soils significantly warmer in the summer. And also invasive earthworms make the soil temperature a lot more variable simply by removing O horizon, which is an excellent heat insulator. So earthworm infested sites have soils that are warmer and more variable soil temperature. So in the trip this summer to Alaska, we also began to listen to the soundscape of soils along the earthworm invasion transect in Alaska. So here, Adrian is bearing this small audiomus, which is basically a microphone that listens to the soil sound in the soil and record it. So, we are interested in knowing how earthworms change the soil soundscape. This is this is a new collaboration that Adrian bridged me to a group at Stanford, and on top of the existing collaboration between me and Jonathan Klaminder in Sweden. So we actually have a good evidence that the earthworms do change the soundscape in the soil. So in this experiment that Sarah Kim and Adrian and Jane and Hannah and Travis and Jonathan conducted in the Arctic Sweden, basically showed that the tundra soils, once they are invaded with earthworms, become louder. And that is because earthworms, by replacing O horizons with the mineral soils, and then the earthworms basically make the soil material more conductive to sound. So this was a really interesting finding to tell us that earthworm invasion may actually have a significant impact on the relationships among the animals living in soils. So coming back to Minnesota, I have been also working with Satoshi Ishii, and in this particular paper that is in revision for soil biology and biochemistry, and Satoshi Ishii's group, and using metagenomic approach, and showing that earthworm invasion substantially changes microbiomes associated with nitrogen cycling. So I'm really glad that Satoshi is here with us today, because if there is any biology questions, microbiology questions, then I will direct it to Satoshi. And Satoshi and I continue to work, and also and we are also working with Paolo Pagliari. And in this project, we like to understand how agricultural management and exotic earthworms interact and affecting soil carbon. So it is quite remarkable how earthworms transport organic matter to subsoils in the agricultural fields in the Southwest Research and Outreach Center. But I also can tell you that the composition of earthworm species and their impact on soil carbon differ quite significantly among organic farming and no-till conventional versus moldboard conventional farming. So I'm really looking forward to more work here with Satoshi and Paolo. And kind of, I continue on the earthworm theme here. So as you may have heard, much part of the US is going through the second wave of earthworm invasion. So following the invasion of earthworms of European origin, then we are beginning to have jumping worms of Asian origin. And they are rapidly replacing those European earthworms and then expanding their territories. So one thing really interesting about the jumping worms is that they dramatically transform the soil structure. So I already mentioned that European earthworms remove O horizon and create a dense A horizon. But that dense A horizon, once they're invaded by jumping worms, become loose and then turn to something like a can litter, as you see in this photograph. So they are extremely loose materials. So if you are walking on the hill slope infested with the jumping worms, then you will feel like you are walking on a very slippery ground because you're walking on these loose materials. So we are doing a lot of applied research on jumping worms. And one of them is to understand the mechanisms they are being introduced and passed around in Minnesota. And we are also looking into what environmental controls affect the population level of jumping worms. So here, Tyler and I are moving around the litter to see how the litter thickness or removal of the litter or addition of the litter affect their populations. And we are also testing several chemicals to see their potential impact on reducing jumping worm populations. Okay, here, now I'm switching gear to mountain farming. And, I started my scientific career by studying mountain or hill slope soil geochemistry. And the photo here is from Feather River, California, where I was coupling landscape evolution and soil genesis. And recently, my group has been collaborating with Blended Toners group to understand kind of more detailed carbon geochemistry of the mountain soils. So those experiences in mountain soils led me to the issue of mountain farming. So for example, Azucena Sierra in my group is studying how indigenous coffee farmers take advantage of the complex mountain landscapes in their organic coffee farming in Mexico. And Azucena's work was also selected as a DIJ project for the Institute on Environment. So on another study that is in a mature level and is relevant to mountain farming is this collaboration with the archaeologist at the University of Hawaii. So we are collaboratively studying how long-term development of economic landscapes in Tau, American Samoa, and how that reflects the feedback between natural constraints and human and societal processes. So I'm going to more specific. So more specifically, we are interested in the unlanded terraces and stone mounds that had been abandoned since the European contact in Tau, American Samoa. So this is a very densely forested landscape, and it's also steep mountain. And this terrain is very difficult to maneuver through because of the dense vegetation. But it is really remarkable that this dense rainforest is also filled with many number of terraces and the stone mounds that reflect active use of the landscapes by the people in Samoa before the European contact. So one of our goals is to find out what controls the spatial distribution and extents of those human-made structures in American Samoa. So here's some of the data we have, and then what it basically tells us is that the soil fertility decreases with elevation in this island. So because of the precipitation increase. And then there is a nonlinear threshold at about the elevation of 300 meters. And then beyond, above that elevation, soils become more acidic and then lose phosphorus and also loses calcium cations. So very interestingly, that 300 meter is a cutoff between the heavily terraced areas versus relatively unused areas in that island. Okay, so I'm gonna talk briefly about teaching and my outreach. So here is my opportunity to advertise my course. In the upcoming spring, I will be offering Lands and Humans in the World Cultures. This is a course developed in collaboration with the university library as an online course. And it is about scientific and historical foundations of land uses in different cultures. And those topics include shifting cultivation in Nagaland and agriculture in tropics versus temperate, the divergence of manure systems in Asia versus Europe, or plow as a driver of social change in Northern Europe versus highly productive Iroquois no-till maize farming, and the rice farming in East Asia, and the mountain indigenous farming in Mexico, etc. So if you're interested, and let me know. And then the second to the last, so earthworms are really good at getting people's attention. So, I already mentioned that I used to study more of the history of geochemistry. But whenever I give a talk about history of geochemistry and then ending 5-minute discussion of earthworms, then all the questions I get are often about earthworms. So earthworms is really a powerful way to talk about science and nature, ecology, and science with the public. So if you ever need a person to chat about exotic earthworms and their impact in Minnesota, in your community, in your schools, or your children's schools, let me know, and I will be happy to come and then give a presentation. So I promise this is my last slide, and that this is something I'm really excited about. So I'm collaborating with South Korean film director to create a series of films on soils. So we just got a funding for the first one, and titled Breathing Land. So it will be premiered during a film festival in South Korea in the spring 2023. So I have written several, but I keep writing scripts for a series of films. So I'm hoping that Netflix may fund it. So I might contact you, contact one of you in the future, for your works and insights into this film project. So thank you so much. And then I would appreciate any questions or comments. Thank you.
All right, thank you, Kyungsoo. There you go, opportunity to be in a film, everybody.
Yeah. I have a lot of questions for many of you. Yeah.
Deborah says you're going to join the ranks of those fabulous South Korean films coming out. Yeah.
I can tell you that, you may remember the movie Parasite. And the director once came to Walker Arts Center, and right after that, he was awarded what was the award? Oscar, yeah. And then so I went there, and then there was a long line, and then I was curious how long the line was. So I walked in. And I noticed that many people stand up, began to applaud, and then so I thought Bong Joon-ho was behind me, but I found that many of them took me as Bong Joon-ho and then stood up. Sorry, yeah, sorry for the joke, but it was true.
Kyungsoo, can I ask a question?
Sure, yeah.
How did you get involved with the film project?
Oh, well, so the film director is actually my high school friend, and is a very dear friend of mine. So when I began teaching lands and humans in world cultures, I got, while I was preparing for the course, I got interested in many, different land use practices in different cultures. So as I was kind of collecting those stories and was learning about them, and I often kind of described what I was learning to my friend who was a film director, and he began to show interest. And then I once asked him almost jokingly whether this is filmable. So that's how we started. Yeah. Yeah. So I'm really looking forward to it, and it looks like it will be a fun project. Yeah. Yeah. So yeah, Brandy, if you like to appear in film, you are in.
No, but I have lots of students in my grad class right now that have lots of experience being recorded while speaking. So
yeah,
I'll put them forward.
Yeah, and our area's graduate students would be awesome to have on the films.
Kyungsoo, this is Satish Gupta. I got a question for you. Very nice presentation. Enjoyed it, both yours and Peter's.
Thank you.
Could you put this thing in the big picture? I mean, everybody knows when we take a basic soils, the soil genesis, there are many physical and biological factors affect. So when you're done, think back, like I am retired and thinking back, what did I do? What do you think you're going to be saying? What did you find, or where are you going?
I'm thinking that this reflects a lot of discussions that I had with Adrian and Tyler too, and particularly on the earthworm work, that that the changes we are seeing are very rapid and also quite remarkable, and they are really making huge changes to the soils and ecosystems in the subarctic and Arctic landscapes. And then those landscapes, used to have, not much bioturbators. So those, Arctic and boreal forest and tundra used to be covered with, thick organic horizons and with minimal development of, A horizons. So we are basically seeing dramatic change that includes the replacement of this mineral-free O horizons by mineral-associated organic matter-filled A horizons. So I think what we are seeing, through the earthworms, basically pointing us to a direction that, in the future world, where carbon cycle in the Arctic is increasingly controlled by their association with minerals. So that's how I see it in our broader kind of geochemical perspective. And then also, the work we do in the mountain farmings, the kind of broader picture we have is this, that, when we, travel around, Great Plains in the US, then we see those big farms and huge farms. And then every year, those farm sizes are getting bigger and bigger at the expenses of the small farms. The kind of that process is basically built on the effectiveness of the larger farms. And if you have a machine, then you have a capacity to farm a large fields. But that does not apply to mountains, because a mountain has, a highly, heavily dissected by the channels and also steep slopes. So those landscapes do not, allow much of the mechanization of the agriculture. So kind of what I see is that those mountain agriculture will probably stay as small farms, long into the future. And then also those, mountain landscapes are the homes and the farm fields for many of the smallholder farmers in developing countries too. And then those are also the places where ethnic diversity and biological diversity are high. So I think there is much to be studied on the mountain agriculture. But then the truth is much of the science we do in soils and also under the new name of the critical zone science have not really ventured into, kind of using soil science to the benefit of those, farmers who are farming those steep slopes. So that's how I see kind of, how, my work is going. Yeah. But thank you for, good question Satish. I appreciate it.
Thank you, Kyungsoo.
Yeah.
Kyungsoo, there's one more question in the chat if you've got
Okay.
time.
Yeah. What are
From
the
Zach. Yeah, do you see it there?
Yeah. What are the implications of soil soundscape changes due to earthworm invasion? So we had a couple of really nice discussion about this. This exact question, even among the authors, because first we started to look at whether we can even record the sound that earthworms make. And then basically what we find is that, the earthworms don't really make huge sounds that are audible. So in that first, question, we don't really have good results. But instead, what we are finding is that earthworms change the physical environment of soil so dramatically that the way that sound propagates through the soil is fundamentally altered. So so what we are kind of seeing as an implication is that we don't really know much about how the animals living in the soils kind of sense each other, kind of interact with each other. And then, for example, if you walk into the forest, then the birds will hear you and fly away. But do animals in soil do the same thing? They will hear some sound and then they move around, and we don't really know much about those basic questions. So, this is kind of beginning of the, big questions, to understand the kind of soundscapes in the soils and how individual organisms can, contribute to it or change it. Yeah. So this is a really good question, Jack, that we are still kind of sorting through, but at the same time, it is kind of inspiring that that we can now begin to listen to soils.
Yeah, it's a fascinating concept. Great talk.
Yeah. Oh, and I have a Deborah's question: is it possible for moisture status to be related to soundscape? So one thing that really puzzled me was, in the paper that I briefly showed, Sarah Kin was the first author, and then Adrian was the second author. They irrigated soils and then see whether that affected the soundscape. But then the irrigation, basically, which affected the soil moisture, didn't change the soundscape very much. Yeah. So that may be because of the high organic matter content in those soils. So I guess that impact is probably soil dependent. But here in this specific experiment, that how the organic matter kind of present, and is it mineral free organic matter, or is it mineral associated organic matter, that seems to have a big impact on soundscape.
Great, thank you so much, Kyungsoo.
Thanks, Kelly. Yeah.
It's a bit after 5, so I will let everyone go, but yeah, I just want to say thanks again to Peter and Kyungsoo for volunteering their talks today. I think these lightning talks are one of my favorites every semester, because I love hearing what all the cool things that everybody is doing in the department. So thanks everyone for coming, and we'll see you next week for Sarah Mattson's talk.
Okay, thanks, and have a good evening. Bye-bye.
Bye.